Welcome back. This last segment, segment number 12, is on linear regression and bivariate data. Now what we're going to be looking at is data that is bivariate. That means it has two parts. In the past, what we have looked at is univariate data, asking somebody his height, for example, and recording heights, or how many glasses of milk the person drank yesterday and recording the number of glasses of milk. This is bivariate data, means that on each object that's surveyed, there are two parts to it. For example, you might ask a person's height and weight. So you would have a pair of data. Then you would go to the next person and ask height and weight, height and weight. And so you have paired two parts, a pair. It's called bivariate data. And what we're going to be studying is if we think that there's a relationship between the two where one depends upon the other. So with bivariate data, we have two related pieces of data. For example, height and weight, they're related to each other. Life expectancy and risk factors. Now in this case, it's probably more than bivariate data. Your life expectancy depends upon your risk factor, but it depends upon many other things also. Now we have salary and education. So do we think the salary that a person earns depends upon the person's level of education, or does the person's level of education depend upon the salary? Well, in this case, the salary depends upon the level of education. Salary also depends upon many other things, and that's what multivariate data deals with, is the many different other items that we have a variable depending upon. But we're going to deal with just the simplest case in this class. That's bivariate data, two pieces of information, and linear regression, where the data follows a line shaped. There are many ways that bivariate data can be related to each other. The linear regression involves a line, though. And if you recall from algebra, we have the function of a line, y equals mx plus b, or we can say y is a function of x. Our independent variable is x, and our dependent variable is y. Now we're going to write this slightly differently. Most software packages will use y equals a plus bx, or y equals b naught plus b1x. Statisticians usually use the second format because then if there is more than one factor, we can have b naught plus b1x1 plus b2x2 plus b3x3. But in the simplest case, a is our y-intercept, and here b is our slope of our function. So just a quick review for the equation of a line. If we have y equals 2 plus 3x, we're going to plot 2 points on the line, we connect it, and we have our line with slope of 3 in this case. Well, let's look at how we would start. The way that we would start before we do any calculations is we would look at the scatter plot of data. So we have data, and we're going to look to see what the data looks like. Now in this case, let's say I plotted my data. Here it looks like there's a positive relationship. As x is increasing, y is increasing. And in fact, in this case, it also looks like we might have a linear relationship. As x increases, we could draw what looks like a line going through to be the line of best fit. The regression line actually has a few names. One is the line of best fit, meaning this is the best fitting line to this data. Another one is regression line, and the least squares line. This one, though, we know has a positive relationship. As x increases, y increases. Now let's look at another one. And in this next case, we're going to have a negative relationship, but not a linear one. So if I were to graph this data right here, I would have maybe this is what the data looks like. Well, a line would be probably like this. Here would be a line going through. But this data really looks like almost the exponential function, where as x increases, y decreases, but we have a relationship that's not linear. Looks more exponential for decay. Let's look at another one here. Let's look at where there's no relationship. Here we might have data that looks like this one. As x increases, as x gets bigger, we can't make any sort of prediction as to what's happening with y. So our line of best fit would probably just be a horizontal line going across here. We have no value or no way to predict. The last case that we're going to look at is one that has a relationship, but it's certainly not linear. Let's look at this data. For this last case, we certainly see that there's some sort of a relationship, but it does not look like a linear relationship. In fact, this one looks like it's going up, and then it's coming down with a long right tail. Maybe an example that might fit this one is if we had the case of age versus how far a person could run without stopping. We might have the young age, person can't run very far. Then we might peak around age 25. And then from there on in, it's downhill. That's why they call it downhill after that. It's all downhill after this part, going down to over maybe about age 90, where a person can run a very short distance. So in this case, we do have a relationship, but it doesn't seem to follow a line. We also have, when we look at these, what are called outliers. If we were to look at this graph of this data, and we have all of these values here, and then we have one value way up here. So here we have a young person that can run marathons around everybody else. This value right here would be called an outlier. An outlier is a value that lies far outside the rest of the data. Now, in general, what people often do is they just disregard the outlier. They take the value out and work as if it never existed. That's not a good idea. You may come to the same conclusion, but you first need to examine an outlier very carefully. It's possible that an outlier holds the key to what it is you're studying. So, for example, let's say you were doing a study with blood pressure dependent upon dosage of a medication, and you had an outlier far outside all the others. Well, it could be that you're deciding that maybe this value just doesn't belong, I'm going to forget about it. It also could be that in certain people, taking a specific dosage of medication raises the blood pressure so high that this gives you information about the danger of that medication. So what you want to do is you want to clearly examine the outlier very carefully. See if it was just put in data that was put in incorrectly, if it's erroneous data, or if in fact it holds the key to everything it is that you're studying. Well, our goal is to come up with a line of best fit. Most of the time, the data does not lie on a perfect line. And so if we look at a new graph here, and we have this line, what we can see is that as x is increasing, y does increase. So as x increases, y does increase, but the line of best fit does not go through all the points. We have to make our best fitting line. Let's say I thought the best fitting line was this one. It's not, but let's just say we thought it was. Well then, for each value of x, here's a point. Actually, I'll use a different value. I'll use this one right here. This one is some value of x and some value of y. Right over here for this point. We'll make it nice and big. This is the actual value of x and the actual value of y. But however, if we were to look at the estimated value for y here, for this value of x, on the line, we would have a point recorded on the line, and this would be for the value of x, what we estimate the y value to be based on this line. So there's a y with a hat on it, y hat, what we're estimating. In between here is our error, how far off we are. So with a bad fitting line, our errors are going to be far off. Some will be negative and some will be positive, but the error is the difference between the estimated value for y and the actual value for y. And since some will be positive and some will be negative, what we do is we square those errors so that they're all positive. And then we have a positive number. The bigger the number, the worse fit the line is. And when we add up all these numbers, we have what's called the sum of the squared errors. If we had data that was a perfect fit, so this is every value lies on the line, then our error would be 0. That almost never happens. When we square the error, though, we get sum of the squared errors, and our goal is to minimize the SSE, or sum of the squared errors. That's our goal. So going back to this graph that we have right here, this is a really poor fitting line because our sum of the squared errors is going to be a large sum. A better fitting line would be to do this line right here. This is a better fit. And how we can tell is that we look at the points. Before, this point was off by a large amount. Now it's off by a small amount. So our SSE is going to be smaller when we add up all the amounts that these values are off. They're off by much smaller amounts. So we'll have a smaller SSE. It's a little bit difficult to find out the actual sum of the squared errors by hand, and you can do it. It involves matrix manipulation, and you'll be able to figure that out if you wanted to put the time into it. But we will do this by doing it on the calculator and coming up with a regression line. Most scientific calculators will have that. Here's an example that we have. This is data from the physician's handbook, and it is data on the average heights for American boys, and it's from the physician's handbook, 1990. And we have age birth, which so the average height is 0, age 2, 3, 5, 7, 10, 14. And here's the average height in centimeters. So I just want to make sure that you realize this is not inches, in centimeters, 50.8, 83.8, 91. Let's see if there's a relationship. So the question that we're asking ourselves is, as boys' age increase, is there a relationship between what happens to boys' height? And so this is bivariate data. We have age and height, and we want to see if we're able to find a relationship between the height and the age. So let's enter our data into whatever program that we're using right here. I'll start off with entering the data into L1 for the age. Let's clear out what we have. And the age, we have 0. Then we have age 2, 3, 5, 7, 10, and 14. And then the heights are 50.8, 83.8, 91.4, 106.6, 119.3, 137.1, 157.5. It seems to me when I look at this that it does seem like there's some sort of a relationship between as boys get older, they get taller. But let's check it out statistically and see if this is actually the case. We're going to quit from here, and we're going to go and calculate our linear regression. Now, if you notice coming down here, there's a linear regression at number 4. This is not the one we want. We want the one that's in the form of a plus bx. And so we have a linear regression, and I'm doing this on the first 2 lists. So I have my data in L1 and my frequency in L2. And what we're told is that the intercept is 65.0876. The slope is 7.0948, meaning every year our expected growth in a boy is 7 inches, or actually 7 centimeters, not 7 inches. And R squared is just the square of R. R is the one we want, which is the correlation coefficient, 0.9761. One of the first things that we should do always is sketch this. So we're going to go into the stat plot right here, the stat plot, and I want to put my plot 1 on. So I'm going to go into plot 1, and I want to draw a scatter plot, which is this first one. The second one is where the dots are all connected. So I'm going to draw a scatter plot. My X is in L1, my Y is in L2, and whatever marking I want to have. The next thing I need to do is adjust my window, and I'm going to go from age 0. You know, I think I'm going to go up to age 30, even though our data ends at 14. And I'll just scale by 5s. And then the Y, we're going to go from 0. And I think I'm going to just go up to 300. And you'll see in a minute how come. And I'll scale by 50s here. And now when I go to graph this, we can see that it certainly does look like there's a relationship between X and Y. As X is increasing, as X gets bigger, Y tends to get bigger also. So certainly we see a relationship. If I wanted to draw the least squares line, I could draw the line that we calculated before. We had the least squares line, and let's just do that once more. Let's go into the graph, Y equals, and in here I'm going to put the variable of the regression line. So I'm going to go down to Y variables. Oops, I'm going to go not there. I'm going to go down to 5, statistics, and I'm going to put in the equation of the regression line in that first one. So if you notice what happened is you could have done this by hand. What came up was the regression equation, 65.0876 plus 7.09x. Now the line is going through. And I can see this is the regression line or the line of best fit. Let's say I wanted to figure out how tall I expected a 25-year-old man to be. Well, we might be tempted to go over to 25 and put 25 in for X. And if we did that, here I'm just going from point to point. Well, if I did that, and now I climb up the line until I get to 25. Oops. Here's the closest we have on the line, 25. I see that my estimated height for a 25-year-old man is 243 centimeters. Well, those of you who are proficient on the metric system are probably realizing that this is a ridiculous number to have a 14-year-old boy estimated height down here and have a 25-year-old going up. In fact, if we continue this to a 70-year-old man, let's do that. What would we expect for a 70-year-old man? I'll adjust the window. We'll go to 70, and now we'll graph it. Oh, we can't even do it based on this. We'll adjust it once more. For a 70-year-old man, here we keep going. Here gets the man. I don't know if you can see the cursor arrowing up, but now I'm 57, 58, well, 59, 60. I'm already up to 493 centimeters for the height. So what I want to point out to you is that there's a real danger in using the regression line. What you need to make sure is that when you use the regression line, that you're only using it within the minimum value for X and the maximum value for X. You want to make sure that the regression line is only good for the lowest value of X to the highest, meaning the line that we came up with, we could use to predict the expected height for a 12-year-old. It's actually the expected average height for a 12-year-old or a 9-year-old, because those are within 0 and 14. We cannot use it to predict the expected average height of a 70-year-old or 75-year-old, because that's outside of the highest value for x that's given. So to summarize this part a little bit, and then we'll go on, to calculate the regression line, it's valid from the lowest value of x to the highest value for x. It's not at all valid outside of that. We should not use the line to predict outside of what our domain is. Domain are the values for x. Sometimes you may read a report that says, if this trend continues, then we expect that by the year such and such, we'll have this many cases of, and something is given. Well, what's being done at that point is the regression equation is being used to predict out to the future. So a regression line or regression curve is being used to say, well, if we were to continue at this trend, there's a caveat in there. But we can't continue at that because we don't know what's going to happen. Now, the next thing we need to do is we need to see, is the relationship significant between the x value and the y value? And we have a chart that deals with the figuring out the significance. On this particular example that we just did, the number of pairs of data that we entered were 7 pairs of data. We had the pair for 0 and 50.8, then 2 and its height, 3, and so on. We had 7 pairs of data. And if you use the chart that's given in your textbook, what you'll see is that the chart is given by degrees of freedom and a critical value. This is figured out at the 95% level. This table is figured out at the 95% level for figuring out when do we consider that there's a strong relationship between the variables. Well, correlation can go from -1 up to +1. If we have a correlation of +1, that means that there is a perfect fit. The points are lining up exactly on the curve that's been the regression curve, and it's increasing. If there's a -1, we have a perfect fit again, and the points line up exactly on a curve that has a negative slope or is decreasing. A correlation of 0 tells us that there's absolutely no relationship between the x and the y values. But most of the time, we're someplace in between. We're someplace in between -1 and +1, and not being at one of these 3 values. So what we need to do is we need to say, for the correlation that we have, do we think that the relationship is significant or not? Well, we go to our degrees of freedom. In this case, we had 7 pairs of data. And our degrees of freedom then are 7, which we put in for n, -2, or 5. 5 degrees of freedom. We go across to 5, and we see that the critical value is at positive and at negative. So there are 2 critical values. They're at positive and negative 0.754. We mark those off on our number line. Here's -1, here's 0. Negative 0.754 would be about here. Negative 0.754. Positive 0.754 would be right about here. We now look at our correlation coefficient and plot that where it fit based on a number line. We had a correlation coefficient of 0.9761. Well, on this number line, 0.9761 falls, here's 0.754, right about here, 0.9761. The area in between the 2 critical values, if a correlation coefficient falls in between these 2, this is considered not significant. That means if the correlation is between negative 0.754 and positive 0.754 for 7 pairs of data, we would consider that the relationship is not strong and that y does not depend upon x. It's not a good predictor. X is not a good predictor, and the line is not a good predictor. We can still calculate it because we can do algebra and arithmetic to calculate it, but it doesn't have much value. If the correlation coefficient is between the lower critical value and -1, then we say that it is significant, and there's a strong negative relationship, meaning that as x increases, y decreases, and it's significant. If the correlation is between positive critical value, 0.754, and 1, again, we say that it is significant. So in this case, our correlation coefficient was 0.9761. So we said that there is a strong relationship between the x and the y values. As boys got older, they got taller. Well, that's not a surprise for this example, but sometimes it doesn't seem to be a relationship, and we find that there is. So for this last section, what we did was we calculated the least squares line. Visually, you want to look at the scatter plot and see, does it look like there's a good fit? If there are any values that lie far outside the others, you want to examine them. If they were incorrectly recorded, you eliminate them. Otherwise, you decide whether or not to keep them in your calculations or not. And then we try to see, is there a strong relationship between the variables? Well, I thought that at this point, you would like to see who are the people who made this class possible. And so we're going to go on a little tour to meet the various people who helped to make this class go on.